Assalamu alaikum. Bismillahirrahmanirrahim. I welcome you to the 15th lecture on advanced computer architecture. Today, I will continue our discussion on instruction level parallelism for dynamic branch prediction. After a brief recap of what we discussed last time, I'll talk about different techniques for branch prediction. Last time, we discussed Tomasello's approach, which Tomasello developed for IBM 360 for high performance operation without any special compiler being introduced for this processing system. So this approach is basically hardware based, where the control and buffer are distributed throughout the hardware. The registers in instruction are identified by pointers or the values in the reservation stations. So this operation is equivalent to renaming the registers. Then, unlike scoreboard, Tomasello can have multiple loads outstanding. We explained this approach with the help of an example. Here in this example, these two properties allow to issue an instruction having name dependence. For example, multiply is issued which has name dependence of register F2. Whereas in cycle 11, as you can see from here, Tomasello eliminates WAR hazard, that is the write after read hazard, as in this example, add writes the result in cycle 11, even if divide will start execution in cycle 16. Then we continued with this example, and at the end, we found that Tomasello issues in order and it may execute out of order. So this is in fact the major advantage of using Tomasello in order to enhance the overall performance of the system. Then in another example of loop to understand the power of Tomasello approach to eliminate write after write and write after read hazards, we considered this loop example, which is shown over here. Here we considered multiplying 10 elements of floating point array in memory to a scalar in register F2. The first element of the array at address 80 is loaded into the register F0 and multiplied by F2. The result is stored back at location of the first element. This sequence is repeated till all the elements of the array are multiplied. Here, the integer instructions subtract, immediate, and branch not equal 0 are executed out of order to evaluate the condition. The prediction branch taken is implemented by repeating the loop instruction as shown in this sample program. Here you can see that in cycle 0, the status is that the prediction branch taken is implemented by 2 iterations of the code shown here in the first half and in the lower half. You can see here that the branch conditions are not shown in this loop, but they will be taken up during the issue behavior. Furthermore, the register R1 has been initialized to the value 80, which identifies the total number of 10 iterations. Then now you can see from its performance in the 6th clock cycle, here load is issued prior to the condition evaluation, which means the second load, which is in fact the next in the pipe, assuming that the branch has been taken. Then you can also see that the subtract and branch not 0 are issued in clock cycle 4 and 5 respectively. The register R1 is updated in clock cycle 6 by executing the subtract instruction in clock cycle 5. F0 never sees the result. Here you can see that the branch condition evaluation is not shown here in these tables, whereas only the status of the next instructions and the reservation stations are shown. Then, as you can see from here, in clock cycle 10, load 1 issued in cycle 1 completes execution in cycle 9, 8 clock cycles for the first time as we assumed in the beginning to avoid the cache miss operation. It writes to F0 in cycle 10. Load 2 is issued in cycle 8. It completes executions in 4 clock cycles per instructions second time. Multiply 1 will start in cycle 11, avoiding right after read hazard. Whereas the store 1 will start execution on the completion of multiply 1 to avoid right after write hazard. Here you can also notice that the subtract instruction completes execution in cycle 10. It updates register R1 to the next instruction. Then continuing our discussion, we observed that in clock cycle 15, as you can see here, multiply 1 execution started in cycle 11. It completes in cycle 14 and write results in F4 in cycle 15. Whereas the store 1 issued in cycle 3 has not yet started. It will start execution in cycle 16, avoiding write after read hazard. Whereas the multiply 2 is completing and it is now waiting for the next operation. Then in clock cycle 18, as you can observe from this slide, multiply 1 execution started in cycle 11 completes in cycle 14. It writes result in F4 in cycle 15. Whereas the store 1 issued in cycle 3 has not yet started the execution. It will start execution in cycle 16, completed in cycle 18. Whereas the subtract 1 issued in cycle 16 updates R1 for next iteration in cycle 18. So this process continues as such. The instructions which are waiting for some other results to avoid write after write or write after read hazards, but they allow other instructions to execute out of order. As you can see from this slide that in cycle 21, the multiply 2 execution which started in cycle 12, it completed in cycle 15, write results in F4 in cycle 16. Whereas the store 2 issued in cycle 8 starts execution in cycle 17 after multiply 2 writes result in cycle 16 to avoid write after read hazard. In the last 3 lectures, our focus has been to overcome the data hazards. We discussed scoreboard technique and the Tomaslow's approach and studied their performance for different cases to avoid data hazards and allow out of order execution. We have already discussed variety of techniques to deal with the branches. For example, we talked about delayed branching, predict branch taken, predict branch not taken, etc. all these schemes which we discussed earlier to deal with the control hazards, they are all static. That is, the action taken does not depend upon the dynamic behavior of the branch. In the last lecture, we considered loop-based example to discuss the Tomasello's approach to overcome write after write and write after read hazards. In this example, we observed that dynamically scheduled pipe can yield high performance provided branches are predicted correctly. Continuing with this, today we will discuss the dynamic branch prediction that results in reducing the time to, number one, determine branch condition, number two, calculate the branch target address. Here in dynamic branch prediction, we will observe that we calculate the branch address quite earlier. Therefore, the overall time for branch prediction is reduced. Now, today we will focus on using the hardware to dynamically predict the outcome of branches. That is, the prediction will depend on the runtime behavior of branches. The prediction changes if the branch changes its behavior during the runtime. The hardware-based techniques for dynamic branch prediction are based on maintaining a branch history table, abbreviated as BHT, or branch prediction buffer. The branch prediction buffer is a small memory portion where the lower portion of the address of the branch instruction program counter value is placed. The memory also contains a bit known as prediction bit. This bit specifies whether the branch was taken or not taken recently. Here, the branches predicted as taken are represented by making this bit equal to 1, and the branches which are not taken are represented by the bit value equal to 0. If branch is wrong, then this bit is inverted. So the branch target address in the prediction buffer helps to reduce the branch delay when the delay is longer than the time to calculate the target address. Secondly, this 1-bit prediction information is a simple hint. It is not a final recommendation or final decision. It may or may not be a correct prediction, as this bit may have been changed by some earlier branch operation. Here we can see it with the help of this example. The problem with this 1-bit dynamic branch prediction technique is that in a loop, 1-bit branch history table will cause 2 mispredictions in a row. 1-bit predictor mispredict at twice the rate the branch is not taken. I will explain it to you with the help of this example over here for a loop, which is, for example, a loop is to repeat certain operations 10 times, and which may be written in a high-level language as for I is equal to 1 to 10. Here, the branch is taken 9 times and is not taken once. Now, when this particular loop is to be used with 1-bit branch predictor, here the behavior is mispredicted twice. Once on the first iteration, because the prediction bit is either initially for not taken or had been flipped for wrong prediction during some previous execution. The second misprediction is on the last iteration. However, when the prediction bit is set for branch taken, because this is always there. So this shows that the performance of one bit predictor is degraded because performance is a function of accuracy and cost of misprediction. The accuracy of a predictor is expected to match the taken branch frequency, which in our previous example is 9 out of 10, which means 90%. But in one-bit prediction, 8 out of 10 predictions are correct, which means that its performance has been degraded from 90% to 80%. So in order to overcome this problem, we have got another technique which is known as the two-bit dynamic prediction. The performance shortcoming of one-bit scheme is overcome by this two-bit scheme, which can further be extended to n-bit schemes for some further enhancements in the performance. We will talk about this in details later on. However, here the prediction is changed only if mispredictions are found 2 times. In case of one-bit prediction, we change the prediction every time we found a misprediction. But in case of a two-bit predictor, we wait for misprediction twice. Here 2 bits are used, which can be encoded into 4 states in a system, where this system is implemented with the help of a counter, and this counter in fact counts the number of times prediction is found correct or prediction is found wrong. And if prediction is found wrong for 2 times, then it changes the state. Here, these 4 states are represented as state 00 or 01 for predict not taken, and it is represented as 10 and 11 for predict taken. You can see from this state diagram over here that in a saturating counter implementation, 2-bit counter saturates at 00 for predict taken, or it saturates at 11 when predict not taken. The counter is incremented when a branch is taken and decremented when it is not taken. For example, as you can see over here, it is changed from 00 to 01 for taken when predicted not taken, and it changes from 10 to 11 for taken when predicted not taken. Here the counter is greater than or equal to half of its maximum values. The maximum values in this case are ranging from 0 to 3. Half of them is equal to 10. This means that the states 01 or 11, then the branch is predicted as taken. Otherwise, that is when these states are less than the half, which is the states are 00 or 10, the branch is predicted as untaken. Now let us try an example of the loop for I is equal to 1 to 10. Here you can see from this table that for I is equal to 1 to 10, if we consider the 0 iteration, that is the previous behavior, when the branch not taken and the next state with reference to the previous state diagram is equal to 1, 1, and the prediction is taken. Then in the first iteration, the present state is 1, 1, branch is taken, therefore the next state remains unchanged. And it changes only at the 10th iteration when the present state is 1, 1, branch is not taken, therefore it changes to a value 1, 0. So this means that in this particular case, the prediction fails only once. Now let us see how we can implement the branch prediction buffer or branch history table. Branch prediction buffer or branch history table is implemented as a small piece of memory, which is usually a cache. This cache is accessed with the instruction address during the instruction fetch stage. If instruction is decoded as branch and predicted as taken, then fetching begins from the target as soon as the program counter is known. Otherwise, sequential execution continues. Furthermore, if prediction is wrong, then prediction bits are changed. In case prediction taken, then the state changes from 1, 1 to 1, 0. And in case prediction not taken, state changes from 0, 0 to 0, 1. Now let us consider the accuracy of branch history table by using 2-bit prediction on some real application. Here we will say branch history table may mispredict because either wrong guess from the branch or it got branch history of wrong branch when indexed the table. I will explain it to you with the help of this example over here. Here we consider the spec 89 benchmark, a branch prediction buffer with 4096 entries, that is the 4K entries, result in prediction accuracy ranging from 99% to 82% or misprediction rate of 1% to 18%. Here in this figure, as you can see that as we try to exploit more instruction level parallelism, the accuracy of branch prediction becomes critical. Here the accuracy of the predictor is shown by increasing the size of the buffer. As you can see from here, for 4K entries using 2-bit branch history table and for unlimited entries using 2-bit branch history table, you can see that simply increasing the number of bits per predictor without changing the predictor structure has a very little impact. So we have to look at some other method to increase the accuracy of the predictor. With this much discussion onto the 2-bit and 1-bit predictors, we will look into some other problem which is existing due to some correlating branches. The 2-bit predictor scheme uses only the recent behavior of single branch to predict the further behavior of the branches, whereas in practice the behavior of other branches rather than only a single branch which we are trying to predict may also influence the prediction accuracy. In order to explain this concept, let us consider the worst case of spec 92 benchmark example for 2-bit predictor. Here you can see that we are assuming that the variable AA is assigned to register R1 and BB is assigned to register R2. You can see on this table that on the left-hand side, we are showing the branch conditions, and on the right-hand side, you can see its assembly language implementation. For example, the behavior of first if, where A is equal to 2, then we have to make it AA value equal to 0. This can be implemented by using this 3-line code, that is subtract unsigned immediate R3, R1, number 2. This means that in fact we are placing a value equal to 2 and comparing it with the contents of register R1 and placing the result in R3. Branch if not equal 0, in fact, gives us that if AA is not equal to 2, then we have to branch, otherwise we do not branch. And the last instruction of this section, which is DADD, that is double word add, R1, R0, R0 means if AA is equal to 0, do not branch. Similarly, the second branch is if BB is equal to 2, then we want to make BB is equal to 0. This can be implemented by using this small 3-line loop, that is subtract unsigned immediate R3, R2, number 2, which means that from the contents of R2, we subtract a value 2 to find that is the value of BB is equal to 2 or not. Then branch if not 0, R3, L2 means branch to BB2 where BB is not equal to 2. Otherwise, BB is made equal to 0. Now, the third one, if AA is not equal to BB, then what is to be done? That is implemented by these two instructions, that is subtract unsigned R3, R1, R2 means that compare R2 with R1, which means that find out whether AA is equal to BB. And branch equal 0 means that is branch to B3 if A is equal to BB, which means that here the behavior of B3 is correlated with the behavior of B1. Here, if B1 and B2 are both not taken, that is the branch 1 and branch 2 are both not taken, that is AA is equal to 0, BB is equal to 0, then the branch 3 is taken. A predictor that uses the behavior of a single branch to predict the behavior of that branch cannot capture this behavior. So we need another type of predictor which is known as the branch predictor. Basically, the branch predictor is based on the hypothesis that the recent branches are correlated, that is, the behavior of recently executed branches affects prediction of current branch. As we have observed over here in the previous example, that the behavior of the branch B1 and branch B2 is affecting the behavior of the branch B3. Now, in the correlating branch predictor, the basic idea is to record M number of most recently executed branches as taken or not taken, and use that pattern to select the proper branch history table. In general, we can say that we can design an MN predictor, which means that record last M branches to select between 2 raised to power M history tables, each with n bit counters. From this point of view, we can say that the old 2-bit branch history table is a 0, 2 predictor. Now, in order to explain the use of correlating branch predictor, we will consider this example. Here in this example, we assume that if D is equal to 0, then make the value D is equal to 1. Otherwise, go to the next instruction, and where the next instruction says that if D is equal to 1, then do this operation. So if we look into the implementation of this example at the assembly language, where D is assigned to register R1, the first branch behavior can be implemented by branch not equal 0 R1 L1, that is branch B1, when D is not equal to 0. And the second instruction, which is add immediate unsigned R1 R0 #1, means branch not taken when D is equal to 1 in this particular case. Whereas the next branch behavior is, which is if the branch B1 is taken, then the next one is add immediate unsigned R3 R1 -1, and the second instruction is branch not equal 0 R3 L2. The branch B2 is corresponding to the D not equal to 1. Working on the correlation predictor, we can represent this information by making some initial assignments to the value D. And for this particular case, let us assign the values 0, 1, and 2 as the initial values for D. And let us see that what are the results when these above mentioned instructions are executed. Here you can see that the correlating predictor gives us the results as shown in this table. For the initial value of D to be equal to 0, the condition test that D is equal to 0, that will be true. Branch B1 is not taken, and the D before B2 in this particular case is equal to 1. Whereas for the second condition, D is equal to 1, that is also true, and the branch B2 is not taken. Whereas this behavior is different in case of the initial value of D is equal to 1. When the initial value of D is equal to 1, the first branch condition is not met. Therefore, branch B1 is taken, and the D before B2 is equal to 1. Therefore, the second condition, that is D is equal to 1, is true. Hence, the second branch is not taken. Whereas, if the initial value of D is equal to 2, then definitely the first branch condition is not true. Therefore, B1 is taken. The D before B2 is equal to 2 in this particular case, which means that the second branch condition is also not true. Therefore, the branch 2 is taken. Here, if B1 is not taken, B2 will not be taken. So this shows that the branch operation of the second branch condition that very much depend upon the status of the previous branch condition. So our standard predictor cannot predict correctly in this case. Therefore, we have to have a correlating predictor for this purpose. I will explain the function of this correlating predictor further with the help of another example here. Now, in order to further explain the function of correlating predictor, let us consider our standard 1-bit predictor, which has got additional 1 bit of correlation. That is, every branch in this case has 2 separate prediction bits. One prediction bit is used if the last branch executed was not taken, the other prediction bit is used if the last branch executed was taken. So the second prediction bit is in fact monitoring the status of the previous branch operation. Therefore, we can write the pair of prediction bits as you can see over here like this, that if last branch in the program is not taken slash prediction if the last branch is taken. So this shows that this pair of bits gives us 4 possible combinations, and these 4 possible combinations are shown over here with the help of this table. The status of the prediction bits is written in the first column. The new prediction based on the last branch not taken is written in the middle column, and the new prediction if last branch taken is written in the third column. Here you can see that the prediction bits not taken slash not taken means that the new prediction if the last branch not taken is not taken, and the new prediction if last branch taken is also not taken. Whereas if the prediction bits are not taken slash taken, this means that the new prediction if last branch not taken is not taken, and the new prediction if last branch taken is taken. Similarly, in the third row, which is taken slash not taken, means that the new prediction if last branch not taken is taken, and new prediction if the last branch taken is not taken. Whereas the fourth case is taken slash taken means that the new prediction if last branch not taken is taken, and the new prediction if the last branch taken is also taken. The action of 1-bit predictor when 1 bit of correlation is written as 1,1 for the above example is shown over here. In this particular table, you can see that the only misprediction is on the first iteration. That is when D is equal to 2, as this is not correlated with the previous prediction. All other predictions are correct. So from this we can conclude that the 2,2 branch prediction buffer uses 2-bit global history to choose from among 4 predictors for each branch address. Here you can see that it is shown in this diagram by 4 2-bit per branch predictor tables, where each prediction table has got 16 entries. There is a 2-bit global branch history table. The branch address is identified by the contents of this table, and the prediction is shown here as the prediction considering the previous status, whether it is not taken, taken, or taken, not taken, not taken, not taken, or taken, taken. The behavior of recent branches select between, say, 4 predictions of next branch, updating that prediction. Here we have discussed dynamic branch prediction with the help of 1-bit branch predictor, 2-bit branch predictor, and correlating branch predictor. We can compare the accuracy of these different types of branch predictors by using the SPEC 92 standard. Here in this graph, you can see that the accuracy of different schemes for 4K entries, 2-bit branch history table, unlimited entries for 2-bit branch history tables, and 1K entries for 2,2 branch history table, that is the correlating predictor. These three types of predictions and their accuracies are shown in three different colors. Here you can see that the impact of correlating branch history table is very high, whereas the difference between due to increase in the size of the branch history table, whether it is equal to 4K entries or it is equal to unlimited, it is not a significant difference. But the difference is quite significant in case of correlating prediction buffer. So concluding over here, we can say that in fact, we can enhance the performance of the system by taking into consideration the correlating branches. These correlating branches can be further taken into consideration by enhancing the branch history table by introducing into this branch history table the target branch address. This block diagram for branch history table with the target buffer is shown over here, where you can see that this arrangement is divided into three fields. One field is known as the lookup area, which is getting information from program counter to instructions to fetch. The second is the predicted program counter, that is the target address. And the third column contains the branch prediction, that is whether it is taken or not taken. It is a single bit information. The number of entries in the branch target buffer are placed over here, and the present value of the program counter instruction to fetch is compared with the contents of this lookup section. If it is found to be equal, then we can say that it is yes, instruction is branch and it can be predicted. Program counter should be used as the next program counter. Whereas if they are not equal, then this means instruction is not predicted to be the branch, therefore predict or proceed normally. Now, summarizing our discussion, we can say that the branch history table contains 2 bits for loop accuracy. The correlation predictors take into consideration recently executed branches correlated with the next one, and the branch target buffer, which we discussed at the end, it includes branch address and predictions. I will continue with this discussion next time to further expand this concept of branch prediction with the help of certain examples. And at the same time, I will also suggest that you please go through some examples given at the end of chapter 3 of your book and try to solve those problems and find out certain points where you can have any difficulty. Then we can discuss those difficulties also in detail. I will stop here with this much discussion today, and I say you Allah Hafiz till next time. Thank you.